Welcome to Nitoria. It's lovely to have you here, truly. Wherever you are right now, whatever corner of the world you've carried this little voice into tonight, I'm glad you came. So let me ask you, before we begin, the question I always like to ask. Where in the world are you listening from tonight? What time is it in your part of the night? Maybe it's late and the house has gone quiet around you. Maybe the lamp beside your bed is still on, throwing soft shadows on the ceiling, and you keep meaning to reach over and switch it off. Maybe you're somewhere it's raining, or somewhere it's perfectly still, or somewhere the day hasn't quite let go yet. Wherever you are, settle in. Pull the blanket up. There's no rush here. There's never any rush in Nitoria. And if you enjoy these slow journeys, these quiet wanderings into one big, strange, beautiful idea, a like and a subscribe really does help this sleepy little channel keep going. Small creators like me rely on your support more than you'd think, and it means a great deal. And to those of you who've already subscribed, who come back night after night, thank you, genuinely. You're part of why this place exists. So that's the only ask of the evening. Now settle in. Here's the thing about tonight. I'll try not to make this so interesting it keeps you awake. But if it does, well, at least you'll have learned something. A fair trade, I think. And if you drift off halfway through, that's perfectly fine. That's allowed. That's even encouraged. The ideas will still be here in the morning. They've been here for a very long time, and they're in no hurry to leave. So you don't have to hold on to every word. You don't have to understand every piece. Just let it wash over you, slow and warm, like the tide coming in somewhere far away. Now, let me tell you something strange, something genuinely deeply strange about the universe, and about what would happen to you if you ever fell into a black hole. Imagine for a moment that you are falling. Not falling in a frightening way, just drifting gently toward one of the strangest objects in all of existence, a black hole. And imagine that someone you love is watching you from a safe distance, far away, through a telescope as you go. Here's what they would see. They would watch you approach the edge of the black hole, the boundary we call the event horizon, and they would watch you slow down, slower and slower. They'd watch the light coming off you stretch and redden, shifting from white to orange to a deep, dying red, like the last embers of a fire going out. And then, here's the part that breaks the mind a little. They would watch you stop. Right there at the edge. Frozen. Hanging in place, dimming, reddening, fading. And you would stay frozen there, from their point of view, for the rest of the life of the universe. Not for a year. Not for 1 billion years. Forever. They would never, ever see you cross. To them, you simply hang at the edge, a fading afterimage, slowly vanishing into the dark, but never quite gone and never quite in. That's so unsettling that the physicists who first studied these objects back in the Soviet Union, the great minds Yakov Zeldovich and Igor Novikov, they had a name for them. They didn't call them black holes, not at first. They called them frozen stars. Frozen because of exactly this, because from the outside, anything falling in seems to freeze at the surface and stay there, suspended for all of time. The name black hole came later, made famous by the American physicist John Wheeler in 1967, but before that, for a while, they were frozen stars. And once you understand why, the name feels almost tender. A thing caught at the edge of forever, never quite finishing its fall. But here's where it gets strange. Truly strange. Because that's only one half of the story. That's only what the person watching you sees. What about you? What do you experience as the one actually falling in? You feel nothing. Nothing at all. No wall, no bump, no sudden lurch, no alarm, no sign whatsoever that you've crossed the most famous point of no return in all of physics. You sail across the event horizon smoothly, silently, feeling exactly the same as you did a moment before. From your point of view, you cross. You're inside. It happened. From their point of view, you never crossed at all. You're still out there, frozen at the edge, hanging in the red light for eternity. And now I want you to sit with the strangeness of that, because it's the whole heart of what we're going to wander through tonight. Two people, the same fall, the same black hole, and they reach completely opposite conclusions. One of them says with absolute certainty she crossed the horizon, she went inside, it's done. The other says with equal certainty she never crossed, she's still out there, frozen at the edge. And here's the part that should make the back of your neck tingle just a little. Physics doesn't say one of them is wrong. Physics doesn't say one of them is fooled or mistaken or seeing an illusion. Physics says they're both right, both, at the same time. There's no secret true answer hiding underneath where one of them gets it correct and the other gets it wrong. The disagreement isn't a mistake. The disagreement is built into the very fabric of space and time itself. That's what we're going to drift through tonight, you and I. Slowly, softly, one quiet mystery at a time. Not the cartoon version of a black hole, the real one. The genuinely beautiful, genuinely baffling one that even the cleverest physicists in the world are still to this very day arguing about. And by the end, I hope you'll feel something I always find oddly comforting, which is that the universe is far stranger and far gentler than the stories we tell about it. But before we go any further, I want to take something away from you, a picture, a wrong picture, because almost everyone carries it, and it gets in the way of the real wonder. When most people think of a black hole, they picture a kind of cosmic vacuum cleaner, a monstrous drain in the middle of space, sucking everything toward it, pulling in stars and planets and light, and anything foolish enough to wander too close. A hungry mouth in the dark. And I understand why. It's a dramatic image, and the movies love it. But it's not true. It's just not how a black hole works. Here's the truth, and it's a lovely one. A black hole does not suck. A black hole's gravity, at a distance, is exactly the same as the gravity of any ordinary object with the same mass. No stronger, no greedier, no special pull. Gravity is gravity. It doesn't care whether the mass is spread out in a glowing star or squeezed into a black hole. From far away, it tugs precisely the same. Let me show you how gentle this really is. Picture our sun right now holding the Earth in its long, slow orbit. And now imagine, just imagine, that someone reached out and replaced the sun with a black hole, but not just any black hole, a black hole of exactly the same mass as the sun. Same weight, you might say, just compressed down into something incredibly small and dark. What would happen to the Earth? Would we get pulled in? Would we spiral down into the drain? No. Nothing would happen. Nothing at all gravitationally. The Earth would keep orbiting exactly as it does right now. Same path, same speed, same year. We'd lose the sunlight, of course. The sky would go dark and cold, which would be its own kind of problem, but the orbit itself wouldn't change by a hair, because the mass is the same, the gravity is the same, and gravity doesn't reach out and grab. It just curves the space around it gently, the way it always has. You only fall into a black hole if you get very, very close. Cross a certain line and yes, then you're committed, but from a distance, a black hole is just an ordinary patch of gravity that happens to be wearing a frightening costume. So let that old picture go. The vacuum cleaner, the drain, the hungry mouth, it was never real. What's real is something far quieter and far more interesting, and I think honestly far more beautiful too. Now you might be wondering, and it's a fair thing to wonder, as you lie there in the dark, how do we even know any of this? How do we know black holes are real at all? They're black. They give off no light. You can't shine a torch on one. They're the most invisible things in the universe, almost by definition. So how can anyone be so confident they exist, let alone describe what it feels like to fall into one? It's a good question. And the honest answer is that for a long time, black holes lived only in the mathematics. They were a prediction. A strange shape that fell out of the equations of general relativity, Einstein's great theory of gravity, and for decades many physicists weren't even sure such things could really form out there in the cosmos. They were almost too strange to believe. But then, slowly, the evidence began to arrive, and it arrived in two extraordinary ways, both within the last decade or so, both of which I find genuinely moving when I think about them. The first came in February of 2016. A team running an instrument called LIGO announced that they had, for the very first time, detected gravitational waves. Now, gravitational waves are ripples in the fabric of space itself, tiny stretchings and squeezings of space that travel outward like waves on a pond when something enormous happens far away. And the something enormous in this case was two black holes, two of them circling each other, falling closer and closer until at last they collided and merged into one. One of these black holes was around 36 times the mass of our Sun, the other around 29. And when they crashed together far across the universe, they shook space so hard that the ripple traveled all the way here and gently, almost imperceptibly, jiggled an instrument on Earth. That signal has a name now, GW1504, the first time humanity ever heard two black holes meet. After all those years of black holes being only mathematics, suddenly here was a sound, a real physical tremor, proof that they exist and that they crash and merge exactly the way the equations said they would. And then came the second extraordinary thing. We took a picture, we actually photographed one. In April of 2019, a project called the Event Horizon Telescope, a network of telescopes spread across the whole Earth, working together as if they were one telescope the size of the planet, released an image. It showed a black hole at the heart of a distant galaxy called M87, and what you could see was its shadow, a dark circle ringed by a glowing halo of hot light, the silhouette of the black hole printed against the brightness swirling around it. The first photograph in all of human history of the edge of a black hole. And then a few years later, in May of 2022, the same project gave us another. This time, a picture of the black hole at the very center of our own galaxy, the Milky Way, the one we live in. It has a name too, Sagittarius A star, we call it, written as Sagittarius A with a little asterisk. It's an enormous thing, around 4.3 million times the mass of our Sun, sitting quietly at the heart of everything, with all the stars of the galaxy, including ours, slowly wheeling around it. And now we've seen it, its shadow, its glowing ring, a real photograph of the monster at the center of home. So that's the floor we're standing on tonight. That's the solid ground. Black holes are not a fantasy. We've heard them collide. We've photographed their shadows. They're as real as the moon, which means that the strange, mind-bending things I'm about to tell you aren't idle daydreams. They're our best, hard-won understanding of objects we now know for certain are out there in the dark. So let's slow right down now and build the picture carefully, piece by piece. Because to really understand why two people can disagree about whether you fell in and both be right, we first need to understand exactly what this edge is. This point of no return, this thing we keep calling the event horizon. Let me start with the most important idea, and I want you to hold it gently as we go. The event horizon is not a wall. It is not a surface. It is not a membrane you could touch or a barrier you'd feel. There's nothing there. No substance, no fence, no glowing line in space. If you were drifting toward it, you would see absolutely nothing marking the spot. It is, instead, something far stranger and far more abstract. It is a boundary in cause and effect itself. A line drawn not in matter but in possibility. Here's what defines it. The event horizon is the surface beyond which not even light can escape. And the reason that matters so much is that nothing in the universe travels faster than light. Light is the cosmic speed limit. So if you're at a place where even light, the fastest thing there is, can't get out, then nothing can get out. No signal, no object, no cry for help, nothing. To escape, you'd have to go faster than light, and you can't. Once you cross that line, every possible path forward, every direction you could ever travel, leads deeper in. Not because something is dragging you, but because the geometry of space and time has tilted in such a way that out simply isn't a direction anymore. That's the point of no return. And here's a precise, lovely way the equations capture where exactly that line sits. For the simplest kind of black hole, a non-rotating one, perfectly still, not spinning, the boundary lives at a distance called the Schwarzschild radius. It's named after Carl Schwarzschild, who worked out the mathematics astonishingly early, and the formula for it is beautifully simple. The radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. You don't need to hold the equation, just hold the meaning, which is even simpler. The more mass a black hole has, the bigger this radius is, and it scales in the gentlest possible way in a straight line. Double the mass, double the radius, triple the mass, triple the radius. Nothing fancy, just steady, even growth. To give you a feel for the scale, here's a number to drift on. For a black hole with the mass of our Sun, the Schwarzschild radius, the size of that point of no return is only about 2.95 kilometers, less than 3 kilometers across the radius. Imagine that. Take the entire Sun, all that mass, all that fire, and the point of no return around its black hole version would be small enough to fit inside a single city. A dark sphere just a few kilometers wide and yet so dense and so warped that light itself can't climb out, and because it scales in that simple straight line, you can work out any of them. 10 times the Sun's mass, about 30 kilometers. 1,000,000 times the Sun's mass. Well, now you're getting something millions of kilometers across. The recipe is always the same. More mass, bigger horizon, in perfect proportion. Now I want to give you one more piece tonight, one beautiful clarification, before we drift on, because it sets up everything that follows. Remember how I said the person watching you sees you freeze at the edge, hanging there forever, never crossing, and how you, falling, sail right through without feeling a thing? For a long time, even physicists found that confusing. They thought maybe something physically stops at the edge. Maybe there's some real barrier there after all. But in 1958, a physicist named David Finkelstein worked out something that cleared the fog. He showed that the event horizon is what we might call a one-way membrane. Things can pass through it inward, in, but never back out. And crucially, the freezing that the outside observer sees, that endless hanging at the edge, isn't a real wall. It's not that you actually stop. It's that the way an outside observer measures space and time, their particular point of view, their particular coordinate system, simply breaks down at that edge. Their map runs out of paper right at the horizon. So from where they stand, it looks like you slow and stop and freeze, but that freezing is a feature of their perspective, not a wall in the world. You, meanwhile, pass straight through the one-way door, inward, smoothly, and the door quietly closes behind you forever. And there it is, already glinting at us. The two stories side by side. The one-way door that you pass through without a sound, and the frozen image of you left behind at the threshold, reddening in the dark for the rest of time. Both true, both real. Neither one a trick. So let's rest here for a moment, you and I. Let's not rush ahead. We've laid the ground tonight, slowly and carefully. We've let go of the old cartoon, the hungry drain that was never real. We've stood on solid evidence, the collision LIGO heard, and the shadows the Event Horizon Telescope photographed, M87, and our own Sagittarius A star, 4.3 million times the mass of the Sun, sitting quiet at the center of home. And we've drawn the edge itself, the event horizon, not a wall, but a boundary in cause and effect, set at the Schwarzschild radius, just under 3 kilometers for a sun's worth of mass, a one-way door first understood by David Finkelstein all the way back in 1958. And we've glimpsed the strange jewel at the center of the whole story, that from the outside you'd freeze at the edge forever, and from the inside you'd cross without feeling a thing. 2 observers, 1 fall. Opposite answers, both correct. So if you're still here with me, still awake in your corner of the night, hold that gently as we go deeper. Because next we're going to step into your own point of view. We're going to feel what it's actually like to fall, to cross that silent edge, and to discover the most beautifully backward truth in all of this, which is that the bigger and more terrifying the black hole, the gentler the crossing. But that's where we're heading next, slowly, softly, when you're ready. For now, though, let me say properly what I should have said at the start. Welcome to Nightoria. It really is lovely to have you here tonight, whoever you are, wherever you happen to be lying right now. Maybe you're in bed with the blankets pulled up, the room dark except for the small glow of whatever you're listening on. Maybe you're on a couch with the lamp still on, or on a long train ride watching the world slide past the window. Wherever you are, I'm glad you came. And I'm curious, honestly, where in the world are you watching from tonight? What time is it in your corner of the night? Leave it down below if you feel like it before you drift off. I love reading where these little journeys reach. And if you enjoy these slow walks through big strange ideas, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me genuinely rely on it. No pressure at all. And to those of you who've already subscribed, who come back night after night to fall asleep here, thank you. Truly, you're the reason this place exists. Now settle in. Get comfortable. There's nothing you need to do here but breathe and listen. If you drift off before the end, that's perfectly fine. These ideas aren't going anywhere. They'll still be here when you wake, patient and waiting, the way they've been waiting for the universe itself. I'll keep my voice low and my pace slow. I'll try, as always, not to make this so interesting it keeps you awake, though if it does, well, at least you'll have learned something beautiful. A fair trade, I think. So picture it again. Slowly, the thing we keep circling back to. Picture yourself falling toward a black hole and picture someone far away, safe, watching you go. You feel yourself sail across the edge without so much as a bump. They watch you slow and stretch and redden and stop. To you, you fell in, to them, you never did. And here's the part that should keep you turning it over as you drift. Neither of you is wrong. There's no referee standing outside the whole universe who can step in and say, no, here's what really happened, here's the true version. In relativity, there simply is no shared single now that the two of you both stand inside. The question, did she cross yet, just doesn't have one answer. The disagreement isn't a gap in anyone's knowledge. It's woven into the shape of space and time itself. Two honest observers, opposite conclusions, both correct. Sit with how unusual that is. We're so used to reality having one answer underneath even when we can't see it. The keys are either in your pocket or they aren't. The water is either boiling or it isn't. But here, at the edge of one of these things, that comfort quietly dissolves. And we'll come back to why much later when we meet the people still arguing about it. For now, just let it be strange. Strange is allowed. Strange is the whole reason we're here tonight. But before we go any further, I want to take something away from you, gently. I want to take away the cartoon because it's been lying to you your whole life, and you deserve better as you fall asleep. You've been told in some form or another that a black hole sucks, that it's a kind of cosmic drain, a vacuum cleaner switched on in the dark, reaching out across space to pull in anything it can find. Planets, stars, light, you. That if one drifted into the neighborhood, we'd all be swirling helplessly down toward it like water down a plug hole. It's a vivid picture. It's also simply not true, and letting it go is the first real gift this subject can give you. Here's the quiet truth. Gravity doesn't know and doesn't care what's making it. Gravity only cares about one thing: mass. How much stuff is there? And where is it? That's all. So imagine, just for a moment, something almost mischievous. Imagine we could reach out and swap the sun. We take the sun away, all of it, and in its place we set down a black hole of exactly the same mass, the same amount of stuff, just squeezed into something dark and tiny instead of bright and vast. What happens to the Earth? Nothing. That's the beautiful anticlimactic answer. Nothing happens. The Earth keeps right on orbiting in exactly the same path it traces now, at exactly the same speed, the same gentle, year-long loop it's been drawing for billions of years. We would not get pulled in. We would not begin to spiral. From 93 million miles away, the gravity of that black hole would be precisely, exactly the gravity of the sun, because the mass is the same. It would be colder and far darker, and that would be the end of us in other ways. But sucked in? No, the Earth wouldn't even notice the difference in its step. A black hole only takes you if you get close, very, very close. Closer than almost anything ever does. From a comfortable distance, it's just another heavy thing in space, pulling exactly as hard as its mass says it should, no more, no less. There is no reaching, no grasping, no hunger. The drain was never switched on, it was never even a drain. Let that one go and feel a little lighter, as you do. So that's what these things are not. Now let me reassure you about what they are, because it would be easy, lying here in the dark, to half wonder if any of this is real at all. If it's just mathematics and imagination and clever people spinning stories. It isn't. We have seen them. Not in some vague, hand-waving way. We have genuinely caught them in the act. In September of 2015, an instrument called LIGO felt the universe tremble. Two black holes far away, one about 36 times the mass of the Sun and the other about 29, had spiraled into each other and merged, and the violence of that collision sent ripples through the fabric of space-time itself, ripples that traveled for over 1 billion years, and finally, faintly, stretched and squeezed the Earth by an amount smaller than a proton. And we felt it. We announced it in February of 2016, the first time humanity ever heard two black holes meet. They are real, and they crash into one another, exactly as the equations had promised for a century. And then a few years later, we did something even more astonishing. We took their picture. In April of 2019, the Event Horizon Telescope, a network of dishes scattered across the whole planet, working together as if they were a single eye the size of the Earth, released the first image ever made of a black hole. A glowing ring of light wrapped around a perfect circle of darkness, the shadow of the monster at the heart of a galaxy called M87. A black hole billions of times the mass of the Sun. And then, in May of 2022, they turned that eye toward home, toward our own galaxy's center, and showed us Sagittarius A star, the 4.3 million solar mass heart of the Milky Way, the one quietly anchoring every star you've ever seen in the night sky, including our own. So these aren't ghost stories. We've heard them collide, we've photographed their shadows. The strange things I'm telling you tonight are built on the firmest ground science can offer. Keep that underneath you like a floor in the dark. As we step into the stranger parts, the wonder is real precisely because the evidence is. Now let's draw that edge a little more carefully before we cross it, because everything that comes after depends on understanding what the edge actually is. We call it the event horizon. And the name is more honest than it sounds, not a horizon you could ever touch or stand on, not a glowing surface, not a shell of anything at all. If you sailed up to it, there'd be nothing there to bump against. It's a horizon, the way the line where the sea meets the sky is a horizon, a boundary in what you can and cannot reach, not a thing made of matter. What makes it special is this: the event horizon is the surface beyond which nothing, not even light, the fastest thing there is, can ever get back out. Cross it, and every possible path forward, every direction you could point yourself, every beam you could shine, leads inward. Not because some force is gripping you and pulling, but because of how the geography of cause and effect bends down there. Outside, you can come and go. Inside, all roads lead in. It's a one-way door. That insight that the horizon is a one-way membrane rather than a wall or a trap came from a physicist named David Finkelstein back in 1958, long before we had any pictures to look at. He realized that the apparent freezing we keep talking about, the way an outside observer sees you hang at the edge forever, isn't a real barrier in space. It's that the everyday way of measuring distance and time, the coordinates the distant observer naturally uses, simply break down there. They stop being able to describe what's beyond, so from the outside it looks like a frozen surface, but from the inside you'd pass right through it, no membrane, no resistance, nothing to feel. And how big is this edge? That's set by something with a long name and a simple soul, the Schwarzschild radius. The size of the horizon depends only on the mass, and it grows in step with it. For every sun's worth of mass, the radius comes out to just under 3 kilometers, about 2.95 to be precise. Pile in more mass, and the edge swells outward in step. 1 sun, 3 kilometers, 2 suns, 6, and so on, neat and linear, like rings widening on still water. A black hole the mass of the sun would have a horizon you could walk across in an afternoon if walking there were possible. The one at the center of our galaxy, those 4-odd million suns, has a horizon millions of kilometers wide. And that difference in size, that simple matter of how wide the edge is, turns out to change absolutely everything about what it would feel like to fall in. It's the secret behind the gentlest, most backward truth in this whole strange story. But we'll cross that edge together in a moment, slowly when you're ready. So let's cross it, let's step off the edge together, in your own frame, and see what happens. You are falling. Not the panicked, flailing kind of falling, but the quiet, gentle kind, the kind you feel in the first second of a dream before you catch yourself. You are falling freely toward the horizon of a black hole, and your hands are still, and your breath is slow, and there is no particular reason, yet, to feel afraid. And here is the first strange thing. When you reach the horizon, when you pass the event horizon of a sufficiently large black hole, there is no local experiment you could perform, no measurement you could make in your immediate surroundings. That would tell you the moment had arrived. None. You could watch a compass needle, tap a tuning fork, check a spirit level, wave a hand in front of your face. Nothing would change. Space-time at the horizon of a large black hole is smooth. Locally, it is unremarkable. You would not feel a wall. You would not hear a sound. There is no membrane to press against, no barrier to puncture, no line painted across the vacuum with a warning label on it. You simply pass through. Or rather, the word through is almost too dramatic. You continue. That is closer. You continue falling, and everything around you feels exactly as it did a moment before. This is a direct prediction of general relativity, not a guess, not a philosophical flourish. The horizon is not a place in the ordinary sense. It is a global causal boundary, a property of the whole geometry of space-time, not something you can bump into locally. It is defined by what can escape versus what cannot, not by any local curvature or force. And locally, at the horizon itself, the curvature of space-time for a sufficiently large black hole is actually quite gentle. It is not a wall. It does not announce itself. Physicists sometimes call this the no-drama horizon, which is, when you sit with it, an extraordinary thing to say about a place from which nothing can ever return. The reason this seems so paradoxical, the reason it conflicts so sharply with intuition, is that we are used to thinking of boundaries as things we can feel. A wall stops you, a fire burns you, a cliff edge is the place where the ground ends. But the event horizon is none of those. It is a one-way causal membrane, invisible, unfelt, existing only as a global fact about which paths through space-time lead outward and which lead inward forever. And from the inside, from your frame, crossing it is locally indistinguishable from floating in empty space. There is a thought experiment that has been at the heart of general relativity since Einstein first turned it over in his mind. Imagine you are in a sealed box, a capsule with no windows, and the capsule is in free fall, dropping toward the Earth. Inside the capsule, you would feel weightless. A coin released from your fingers would not drop. It would hang there, drifting. There is no force you can feel that distinguishes this from floating far out in deep space, away from any gravity at all. The elevator and the empty universe feel the same from inside. Einstein called this the equivalence principle, and he considered it one of the most beautiful and productive ideas he ever had. Free fall and weightlessness in empty space are locally equivalent. You cannot tell them apart by any experiment you perform in a small enough region over a short enough time. Now apply that to the horizon. You are falling freely through the event horizon. You are in free fall, in a sense, even purer than the falling elevator, because there is no floor coming, no abrupt end to the analogy. And the equivalence principle says, locally, this should feel like floating in empty space. No drama, no announcement, no stamp in your passport. This is the no-drama smooth horizon, and it is the foundation of everything we will say about the Infala's frame. It is also, as it turns out, what gets challenged later in the evening, but we are not there yet. For now, the picture is clean. You fall through, you feel nothing unusual, and you are inside. But here is where the story earns its strangeness, because what you feel as you cross is not actually the same for every black hole, not even close. And the difference comes from a property so simple and so beautifully backwards that it deserves to be said twice. The more massive the black hole, the gentler the crossing. Say that again. The bigger the monster, the kinder it is at the threshold. This feels wrong. This feels like it ought to be exactly the reverse. More mass, more gravity, more force, more danger. That is how gravity works for ordinary objects. But for a black hole, there is a subtlety hiding in the geometry. And once you see it, you cannot unsee it. The dangerous thing about falling toward a black hole is not gravity in the simple sense, it is tidal force. The tidal force is the difference in gravitational pull between one part of your body and another. Your feet, if you are falling feet first, are closer to the center of the black hole than your head, so the gravity pulling your feet is slightly stronger than the gravity pulling your head. That difference, that gradient of pull across the length of your body, is what does the damage. It stretches you lengthwise while squeezing you crosswise, like pulling on both ends of a piece of dough. The more severe the gradient, the more severe the stretching. Now here is the critical geometry. The tidal force at the horizon of a black hole scales as the mass divided by the cube of the Schwarzschild radius. And we said earlier that the Schwarzschild radius grows in step with the mass. That means the tidal force at the horizon scales as 1 over the mass squared. Write it out and the mass squared sits underneath, on the bottom, making the tidal force shrink as the mass grows. The bigger the black hole, the weaker the tidal force at its horizon. Double the mass and the tidal force at the horizon drops to 1/4. Make the black hole 10 times more massive and the tidal force at the horizon is 100 times weaker. Make it 1,000,000 times more massive, and the tidal force at the horizon is 1,000,000,000,000 times gentler. This is not an approximation. This is what the mathematics of general relativity insists on. So the enormous black hole, the supermassive one, with the ferocious reputation, has a horizon that is locally almost peaceful, and the small black hole, the compact and modest-seeming one, has a horizon that will tear you apart before you ever reach it. This is the backwards truth at the center of the whole crossing story. Let's be precise about what tearing apart means, because it has a wonderful name. And the name itself came from a book on a shelf in a great many homes. When the tidal gradient across your body becomes large enough, the difference in pull between your head and your feet exceeds what the material strength of your body can resist. You are elongated, stretched, pulled thin. The technical name for this process is tidal disruption, but Stephen Hawking, in A Brief History of Time, described it with a word that is far more memorable. He called it spaghettification, and occasionally he called it the noodle effect, which has its own kind of gentle academic charm. You are pulled into a long, thin strand, narrowing and elongating at once, stretched in the radial direction while compressed from the sides, a human noodle drawn out toward the center. Hawking wrote about it with that characteristic blend of precision and wry understatement that made his book so readable, and the word stuck, spaghettification. It is now in the vocabulary of physics and in the vocabulary of anyone who has ever been curious about black holes at bedtime. For a small black hole, spaghettification does not wait for you to arrive at the horizon. It begins well outside it. Consider a black hole with a mass about 10 times that of the Sun. Its Schwarzschild radius, the width of its horizon, is roughly 30 kilometers, about the width of a small city, end to end, and the tidal force from a black hole that compact rises steeply as you approach. Calculations put the fatal stretching zone for a human body not at the horizon itself, but at thousands of kilometers out from the center, far above the 30-kilometer horizon. You would be torn apart, strand by strand, long before you reached the edge. By the time the horizon was in front of you, there would be no longer a you in any recognizable sense. The crossing would happen, the geometry would funnel the remnants inward, but you would not be there to notice. You would have been, in the most literal sense, unraveled. This is a grim picture, but it is an honest one. Small black holes, stellar mass black holes, the kind formed when a massive star collapses and dies in a supernova, kill you before they claim you. They are ferocious at the threshold. The death is not at the boundary, the death is above it, in the space that looks like ordinary space, a region where you might, at a glance, think you were still safe. And then there is Sagittarius A, and everything is different. Sagittarius A sits at the center of the Milky Way, our own galaxy. It is the supermassive black hole that every star in this galaxy orbits around, some closely, some from vast distances. It is about 4.3 million times the mass of the Sun. Not 4,000, not 400,000. 4.3 million solar masses packed into a region defined by its Schwarzschild radius, which comes out to roughly 12 million kilometers. 12 million kilometers. That is about 17 times the radius of the Sun itself, or, to put it another way, a sphere that would comfortably contain the orbit of Mercury around the Sun with room to spare. That is how large the horizon of the black hole at the center of our galaxy is. And at that horizon, the tidal force, scaled by the inverse of mass squared, is gentle. Not just reduced, genuinely gentle. A human body in free fall through the event horizon of Sagittarius A, in a non-rotating idealized model of it, would experience tidal forces far below the threshold of spaghettification. You would not be stretched. You would cross intact. Every cell in your body, every bone, every nerve, every quiet thought you are having would continue undisturbed as you pass through the largest and most definitive boundary in the local universe. You would not feel it. A boundary that no one has ever returned from, that no signal can cross outward from, that defines the edge of the observable interior of one of the most massive objects within tens of thousands of light years, and you would glide through it like walking from one room into another. No door, no threshold you could touch, no sensation that the universe behind you had just permanently and irrevocably become inaccessible. There is something quietly vertiginous about this, the most dramatic thing the universe contains, and from the inside, at the moment of crossing, it announces itself as nothing at all. But what comes after the crossing is where the story gets warmer and stranger and more finite. You are inside now. You have crossed the event horizon of Sagittarius A, intact, unhurt, feeling nothing but the gentle free fall that has been your companion all along. And the question becomes, how long do you have? For a non-rotating black hole of that mass, the interior freefall time from the horizon to the singularity comes out to roughly 19 seconds, about 19 seconds of experienced time in a non-rotating idealized model of Sagittarius A. Not an instant, not a flash, not the sudden and immediate annihilation that the popular imagination tends to assign to crossing the horizon. 19 seconds, long enough to take about 4 slow breaths, long enough to notice the stars or where the stars were, though the view from inside is extraordinary and strange in ways we will come to. Long enough to have one coherent thought. This is a real, finite, experienced duration. It is not long, but it is not nothing. And the singularity, when it comes, is not, in this idealized picture, something you can steer around or navigate away from. But that is for a little later in our journey. For now, just hold on to those 19 seconds. Hold on to the quiet, the intact body, the gentle crossing. Because that is the infowler's side of the story, and it is remarkably, unexpectedly, almost tenderly serene. Now here is the thing about this serene picture. You probably suspected a catch was coming, and there is, but it is not the kind of catch that undoes anything. It deepens it. It takes the serenity and shows it alongside something completely different, something that is equally true, equally rigorous, and almost impossible to hold in the mind at the same time as the first picture. Because while you are crossing quietly, while your 19 seconds are ticking calmly away, someone watching you from a safe distance is seeing something else entirely. Someone watching from far outside the black hole, hovering in comfortable orbit at a distance where the curvature of spacetime is gentle and clocks run at an ordinary pace, is watching you approach the horizon. And what they see is nothing like what you feel. What they see is you slowing down. Not just slowing in the way that objects slow when they move away from something, slowing in a deeper, more fundamental way. The light you emit, the photons that carry your image across the universe back to them, is climbing out of a gravitational well that grows deeper and steeper the closer you get to the horizon. And as photons climb out of deeper and deeper gravity, they lose energy. They stretch. They redden. The photons that carry a blue image of you become green, then yellow, then red, then infrared. Then they slide out of the visible spectrum entirely into wavelengths no human eye could detect. At the same time, the rate at which those photons arrive at the distant observer slows down. Each successive photon has to travel from a slightly deeper point in the gravitational well, and the journey takes fractionally longer. The intervals between signals arriving at the observer stretch out. Your image becomes not just dimmer and redder, but slower. Your movements, seen from outside, appear to lag. Your hand, if you raised it in a wave, would appear to the distant observer to rise with agonizing slowness, each moment of the gesture passed out across longer and longer intervals. This is gravitational time dilation. Clocks run slower in deeper gravitational fields, not as an illusion, not as a trick of perspective, but as a real, measurable, verified fact. Clocks deeper in a gravitational well genuinely tick slower relative to clocks higher up. The ratio between them is given by a factor that depends on how close you are to the Schwarzschild radius. As you approach it, that factor does not just increase, it diverges, it grows toward infinity. At the horizon itself, from the perspective of the distant observer, time appears to stop entirely. And this is not hand-waving, this is not a vague claim that time does weird things near black holes. Time dilation is one of the most measured, most confirmed predictions in all of physics. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, set up an experiment in a building on campus. They sent gamma rays from the basement to the top of a tower, a difference in height of about 22 meters. 22 meters, not 1,000 kilometers, not a light year, 22 meters of ordinary building, and the gamma rays climbing those 22 meters lost a tiny but precisely measurable amount of energy to the gravitational field. They redshifted. The signal was so delicate that the experiment required extraordinary precision, and yet Pound and Rebka measured it, real gravitational redshift over a staircase. The GPS satellites circling overhead right now carry atomic clocks, and those clocks run fast compared to clocks on the surface because the satellites sit higher in Earth's gravitational field and experience less time dilation. The correction is about 38 microseconds per day. If the GPS system did not account for this difference, the positions it calculated would drift by kilometers within hours. The engineers who built the system incorporated Einstein's predictions directly because they had to. General relativity is not an abstraction here. It is an engineering specification. So when we say that someone falling toward a black hole appears from the outside to slow down and freeze, we are invoking the same physics that makes your phone tell you where you are. We are invoking something measured in a Harvard stairwell and baked into every satellite navigation system on Earth. The effect is real. The extreme version, near the horizon, is just the extreme limit of a verified and prosaic truth. And near the event horizon, the extreme limit is truly extreme. The redshift factor goes as 1 over the square root of the quantity 1 minus the Schwarzschild radius over your current radius. As you approach the horizon, as your radius descends toward the Schwarzschild radius, the quantity inside the parenthesis shrinks toward 0, and the whole factor blows up toward infinity. The energy of the photons you emit shrinks toward 0. The rate at which those photons arrive at the distant observer slows toward 0. Your image to them becomes exponentially faint, exponentially stretched in time. For a stellar mass black hole, this practical extinction happens astonishingly fast in the distant observer's time. Not over eons, not over years. Within a fraction of a second, the image fades below any practical threshold of detection. The photons still arrive, in principle, forever, because the asymptote is never fully crossed. But in practice, in any real measurement, the light goes dark almost instantly from the outside view. You become, within moments, invisible. And yet formally, in the mathematics of the distant observer's coordinate system, you never quite reach the horizon. The asymptote is real. The freeze is real in those coordinates. You slow and redden and dim and approach the boundary on a curve that never quite touches it. This image, this picture of the infala dimming and freezing at the edge of the horizon like a photograph of a moment that never ends, is actually what gave black holes their first scientific name. Not black hole, That name came later. Before that, among a group of Soviet physicists in the mid-20th century, the objects were called something that fits this picture exactly: frozen stars. The physicists Yakov Zeldovich and Igor Novikov, working in the Soviet Union, used the term frozen star to describe what general relativity predicted. From the outside, matter falling onto a collapsing star would appear to freeze at the surface, never quite crossing, suspended in an eternal last moment, reddening into invisibility. The star would collapse, and to an outside observer, the collapse would never quite complete. The matter would seem to hang there, ghostly and fading, frozen in the very act of reaching the horizon. John Wheeler, the American physicist, was one of the people who pushed the field toward the name we use now. In 1967, at a conference in New York, he started using the term black hole, and it caught on so quickly and so completely that it displaced everything else. Black hole, simple, evocative, exactly right for the object that not even light escapes from. Wheeler had a gift for naming things, and this was one of his best. But Zeldovich and Novikov had captured something true. From the outside, the object does look frozen. The star's surface, or in our story, your body, hangs at the edge of the horizon for what is, in the outside observer's coordinate time, forever. The image never crosses, it just fades and reddens and dims below the noise and effectively vanishes from the observable universe. So here are two pictures of the same event. From your frame. A gentle crossing. Nothing felt. 19 quiet seconds inside. An ending that comes not at the boundary but deep within. From their frame. A slowing, a reddening, a freeze at the edge. An image that dims to nothing, and in principle hangs there for the rest of the universe's life. And both of these pictures are correct. They are not two different descriptions of two different events. They are two different but equally valid descriptions of the same event, viewed from different reference frames, in a universe where there is no absolute universal now that both observers share. This is the heart of it. This is what general relativity means when it insists that both frames are correct. In Newtonian physics, there was a cosmic clock, one universal time ticking the same everywhere, so that did she cross the horizon yet would have a definitive answer that all observers would agree on if only they could compare notes. Einstein took that universal clock away. He replaced it with a universe where time is local, where simultaneity is relative, where at the same moment is not a phrase that has observer-independent meaning when the observers are separated in a curved spacetime. So, did she cross the horizon? Does not have a single correct answer. It has two correct answers, one for each observer, and neither is more real than the other. Physics does not privilege one frame. The infallible and the distant observer are equally good observers doing equally valid measurements and reaching equally true conclusions. The infallible crosses. The outsider watches her freeze. Both are right. David Finkelstein understood this in 1958. He developed a way of describing the space-time around a black hole that does not break down at the horizon the way the earliest coordinate systems did. The Schwarzschild coordinates, the ones that the distant observer naturally uses, develop what mathematicians call a coordinate singularity at the horizon. They simply stop working there, the way that compass bearings become meaningless if you try to navigate to the geographic North Pole. The breakdown is in the map, not in the territory. Finkelstein found a different map, one that covers the horizon smoothly, and in his coordinates the infalling observer crosses without difficulty, and the horizon is clearly a one-way membrane through which you pass inward, but through which no signal can travel outward. The freeze the distant observer sees is a feature of the coordinates they naturally use, not a feature of the physical space-time itself. The infallible does not slow down and stop in any absolute sense. She crosses. The coordinate system simply fails to describe her doing so in a way that the distant observer can use. And yet the freeze is what the distant observer truly measures. They truly see her slow and dim and halt. That measurement is not wrong, it is correct for their frame. The coordinate artifact is not an error in their observation. It is the natural consequence of the fact that no light can cross the horizon outward, so no news of the crossing can ever reach them. The last image of the infala hangs there because it is literally the last image that could escape. Nothing after it can. This reconciliation, the two frames both correct, the freeze real for the outside observer and unreal for the infala, is the no shared now at work. There is no global coordinate system that smoothly covers both regions, inside and outside, in a way that both observers would call natural. The geometry of space-time near a black hole is such that the inside and the outside are causally disconnected. The infala's frame and the outsider's frame are not just different perspectives on the same stage. They are perspectives that cannot, even in principle, be compared in real time. The outsider can never receive a message that says, "I crossed." The infala can never receive a message that says, "We see you frozen." The incompatibility is built into the causal structure of space-time itself. And this, it turns out, is not a bug. For a long time, some physicists thought it might be a problem, a sign of inconsistency, a place where the theory was saying something contradictory. But it is not. It is what the theory is actually saying. Two observers, separated by a causal horizon, reach different conclusions about the same event because they are in genuinely different causal universes once the horizon is in place. Their conclusions are not inconsistent. They are simply about different things from different places measured in different coordinates, and there is no experiment either of them can perform that would reveal a contradiction, because no contradiction exists. Leonard Susskind and Gerard 't Hooft, working in the 1990s, gave this a name and a formal framework. They called it black hole complementarity. The idea is that the two descriptions, the infala's smooth crossing and the outsider's freeze and fade, are complementary in a deep sense. Like the wave and particle descriptions of light in quantum mechanics, each is valid in its own domain, and no single observer can ever access both at once. You cannot be both inside and outside the horizon to compare notes. The complementarity principle says this is not a problem with the theory, it is a feature of the geometry. The infala's experience is real, the outsider's observation is real, neither cancels the other out. No experiment can force a contradiction between them, because no experiment can be conducted by an observer who is simultaneously inside and outside the horizon. And so the question, did she really cross, dissolves not into confusion, but into a kind of clarity. The question itself was asking for something the universe does not provide, a single, observer-independent account of events that straddle a causal boundary, take away the assumption of universal simultaneity, take away the assumption of a cosmic clock that everyone agrees on, and the question becomes not unanswerable, but unnecessary. There is no fact of the matter beyond the two frames. Both are the whole story, from where each observer stands. This is general relativity working as it was designed to, and it is one of the quietest, most unsettling things the theory says, because it means that some of the most profound events in the universe, the actual crossing of the point of no return, are not events anyone could ever simply agree on. End mid-arc, the narration settling gently on that image. Two observers, two truths, no contradiction. And ahead of us, still the question of what it looks like from the inside once the crossing is done, and the even stranger question of whether the physicists who built this comfortable complementary picture are, perhaps, wrong. And yet, before we follow her inside, let's stay out here for a little while longer, because there is something happening on the outside that deserves its own quiet attention. Something that is, in its own way, just as strange as anything that happens within. Let's talk about what you would actually see, not what you'd feel, not what she'd feel, what you, watching from a safe and enormous distance, would observe as someone fell toward the event horizon of a black hole. And to understand it properly, we need to start with something that sounds almost mundane: the way clocks tick. Imagine two identical clocks. You start them at exactly the same moment, set them side by side, confirm they are perfectly synchronized. Then you take one and lower it down, not into a black hole, not yet, just lower it a little, closer to the surface of a heavy object, a planet say, and you leave the other one up where you are. After some time you pull the lower clock back up and compare the two. They don't match anymore. The lower clock has ticked fewer times. It has run slower, not because anything went wrong with it, not because of vibration or temperature or interference, but because time itself ran slower where it was, in the deeper part of the gravitational field. This is gravitational time dilation, and it is not a quirk, not a theoretical curiosity, not an artifact of unusual measurement. It is a real, measured, verified fact about how time works in our universe. Gravity does not merely bend space, it bends time. The deeper you go into a gravitational well, the slower time flows for you relative to someone higher up. The effect is small at everyday scales, almost laughably small, but we can measure it. We have measured it. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, designed an experiment inside Jefferson Laboratory to measure exactly this. They sent gamma rays up a tower just 22.5 meters tall, not 22 kilometers, 22 meters, the height of a modest building, and they detected the tiny shift in the photon's energy caused by climbing that minuscule distance out of Earth's gravitational pull. The signal was so faint that detecting it required extraordinary care and precision, but they found it, measured it, confirmed it. The gravitational redshift was there, exactly as general relativity predicted, 22 meters, and time dilation was real enough to measure. Now, carry that finding with you and scale it up. Scale it up until you are no longer on Earth, no longer near any ordinary planet. You are floating in space, far from a black hole, watching a friend descend toward the horizon. And the clocks that were ticking together when she started are now, from your vantage, drifting apart in a way that makes the Pound-Rebka shift look like a rounding error. The closer she gets to the horizon, the slower her clock ticks from your perspective. Not slightly slower, dramatically slower. As she approaches the Schwarzschild radius, the dilation factor follows a precise mathematical relationship. The redshift factor for light escaping from a radius r is given by 1 over the square root of 1 minus r sub s over r. When r is large, that factor is close to 1. Everything normal. As r shrinks toward r sub s, the denominator shrinks toward 0 and the factor grows toward infinity. Infinity. What this means practically is that as she approaches the event horizon, you see her clock ticking slower and slower and slower, approaching a complete halt. She does not cross the horizon in any finite time that you observe. From your frame, the crossing never happens. It is asymptotic. It approaches completion forever and never quite arrives. This has a very concrete observational consequence which is worth sitting with. Every signal she sends you, every pulse of light that leaves her position and travels outward toward you, leaves from progressively deeper in the gravitational well and has to climb progressively harder to reach you. Each successive photon is stretched a little more. The wavelength grows longer. What started as visible light shifts toward red, then deep red, then infrared, then radio waves, then wavelengths so long they carry essentially no energy at all, and the pulses arrive at your detector more and more slowly, because each photon, leaving slightly closer to the horizon than the last, takes slightly longer to fight its way out. The gaps between signals stretch. She appears to move in slow motion, then slower, then she stops. She doesn't fall through, she just hovers there at the edge, reddening, dimming, becoming less distinct. Her image spreads across the surface of the horizon like a photograph left too long in the sun. She does not vanish with a pop or a flash. She fades. The light coming from her position grows so faint, so red, so spread out, that within a fraction of a second of your time, she has effectively disappeared from the observable universe. Not because she is gone in any violent sense, but because the last light she ever sent you is still technically arriving, stretched across an infinite future, so attenuated it contains almost no information at all. The fade is exponential. For a stellar mass black hole, a few solar masses, the object dims to practical undetectability in milliseconds of your time. You couldn't hold a vigil. By the time you looked away and looked back, she'd already passed from visible to infrared to radio to nothing. And yet, in the formal mathematics, in the exact equations, the image never quite vanishes. It is still there, infinitely redshifted, infinitely faint, frozen at the edge. Formally, you would need infinite time to receive all the photons she ever emitted after a certain moment. And so in a precise sense, she hangs there at the horizon for the rest of the universe's life. Two things are true simultaneously. She fades to invisibility in milliseconds, and her image technically persists forever. This is not a contradiction. Both are accurate. The asymptotic approach is real, and the practical disappearance is also real. They coexist because one describes what you can measure, and the other describes the mathematical structure underlying the measurement. And here is something worth knowing. Physicists knew about this effect long before the term black hole existed, long before it became a fixture of popular imagination. In the Soviet Union, during the middle of the 20th century, two physicists named Yakov Zeldovich and Igor Novikov were among those working through the mathematics of gravitational collapse. They understood what a distant observer would see. They understood that an object falling toward a collapsed star would appear from outside to slow and redden and freeze at the surface, to halt, suspended at the boundary. And so they called these objects by a name that reflected exactly that exterior appearance. They called them frozen stars. Not black holes, not singularities, not cosmic vacuum cleaners, frozen stars, because that is what you saw when you looked. A star, or the remnant of one, with matter frozen at its surface, perpetually suspended at the moment of crossing. The name was descriptive. It was, in its own way, accurate. From the distant observer's frame, the matter really is frozen there. The exterior picture really does show an object that never quite completes the fall. Then in 1967, the American physicist John Wheeler gave a talk in New York and used a different phrase. He hadn't invented it, but he helped it stick. He called them black holes. And the name spread because it captured something different. Not what you saw, but what you couldn't see. Not the frozen exterior, but the causal interior. Not the appearance, but the structure. Both names capture something real. The frozen star captures the view from outside. The black hole captures the causal geography. And the fact that two names could be given, emphasizing two different true things, is itself a hint at how much the two perspectives diverge. But let's be careful now, because this is where things become easy to misunderstand. And the misunderstanding, if you carry it forward, muddles everything that comes after. The slowing, the reddening, the freeze that you observe from outside, is that the truth of what happens? Is she really frozen there? The tempting answer is to say yes. You measured it, the clocks confirm it, the photons arriving at your detector show her image slowing and halting. What could be more reliable than an observation? But here is what David Finkelstein worked out in 1958, before the term black hole existed, before most of the modern machinery was in place. The coordinate system you are using, the mathematical framework that describes space and time from the distant observer's perspective, simply breaks down at the horizon. Not because something dramatic happens there in any local sense, but because the coordinate you are using to label distance, the radial coordinate, is built around your clock, your time. And your clock, synchronized to your distant position, assigns infinite time to events that happen at the horizon. It is a little like trying to describe a meeting that happens at the international dateline using a single time zone. If you declare that the whole world runs on New York time, then events on the other side of the dateline get assigned times that look strange, times that appear to skip across midnight, times that seem to imply the meeting happened simultaneously yesterday and tomorrow. The strangeness is not in the meeting, it is in using an inappropriate coordinate to describe it. Finkelstein showed that the event horizon of a black hole is what mathematicians call a one-way membrane. Things can pass in, nothing passes out. And from the infaller's side of things, the crossing is perfectly smooth, locally unremarkable, a continuation of what came before. But from the distant observer's coordinates, the horizon sits at what that coordinate system assigns as infinite time. So the crossing looks, in those coordinates, like it takes forever. The mathematics simply doesn't have a way to represent the crossing moment within the distant frame's natural language. The freeze is real in the sense that it is what you genuinely observe. The light really does redshift. The clocks really do appear to slow. Your instruments confirm everything. But the freeze is, in another precise sense, a coordinate artifact. The horizon is not a wall, not a physical barrier. Nothing locally catastrophic marks it. The geometry of space-time is smooth there. The infaller passes through in her own frame without any measurement she could make in a small region, announcing to her, "You have crossed. Something has changed." The dramatic appearance from outside reflects the structure of the coordinate system as much as it reflects anything physically special about the location. This is a subtle distinction, and it is worth sitting with for a moment, even if the weight of it settles in slowly. Your observation is real, her experience is real, neither is an illusion. The coordinates you're using are one valid way to describe the situation. Her coordinates are another valid way to describe the same situation. They give different answers to the question, when does the crossing happen? Because they are measuring time with different clocks in different locations, and in general relativity, those two clocks are simply not interchangeable. And this brings us to the deepest, most unsettling piece of what general relativity actually says about this situation. There is no global now that both of you share. In ordinary life, in the framework of classical physics that served us well for centuries, time was treated as a universal backdrop. Whatever now meant for you, it meant the same thing for everyone else in the universe. There was one clock, in a sense, ticking the same for everyone everywhere. Newton believed this. It was the foundation of how physics was done. Einstein dismantled it, first with special relativity in 1905, which showed that simultaneity is relative even between observers moving at different speeds in flat space-time, and then with general relativity in 1915, which extended that relativity into curved space-time, into gravity, into the structure of the cosmos itself. What this means concretely is that the question, "Has she crossed the horizon yet?" asked from your position out in space, is not a question with a single answer that the universe enforces. It is a frame-dependent question. You, with your clocks and your coordinates, have your answer. She has hers. There is no third clock, no cosmic referee, no omniscient perspective from which to settle the dispute. The universe does not provide one. This is not a failure of our instruments or our cleverness. It is not a gap in our understanding that will eventually be filled with the right equation. It is a feature of the geometry of space-time itself. The events in question, the moment of crossing, straddle a causal boundary in a way that makes them inherently inaccessible to a single, unified description. Think about what this means. You are watching from a safe distance. You see her slow, redden, freeze at the horizon. From everything you observe, she is perpetually suspended at the edge, her last photons trickling toward you across an infinite future. She is, from your frame, never inside. She, from her own frame, has crossed, has entered, is already falling toward the interior, living her final seconds, experiencing what is on the other side of the boundary you can see from outside. You will never receive a message from inside confirming this, not because she didn't write it, but because the causal structure of the black hole geometry means no signal can travel from inside to outside. The event horizon is exactly that boundary, the line past which no information can travel outward, not because the signal would be too faint or too slow, because the space-time paths all slope inward from inside the horizon. There is literally no path a photon could take from inside to reach you outside. So she crosses and she sends you no word, and you see nothing change at the edge, and from your frame she is still there, still frozen, still hanging in the reddening light. And you are both right. This is black hole complementarity, the framework Leonard Susskind and Gerard 't Hooft developed in the 1990s to make formal sense of exactly this situation. The two descriptions, yours and hers, complement each other. They apply to different regions of space-time accessible to different observers. They cannot be directly compared because no observer can be in both places simultaneously to run the comparison. And because they cannot be directly compared, they cannot contradict each other. Susskind and 't Hooft were not just saying, well, perspective is everything, don't worry about it. They were making a precise technical claim that the two descriptions are consistent with each other and with all of physics, provided you take seriously the impossibility of any observer being both inside and outside the horizon at once. The causal structure of the black hole enforces the consistency. The geometry is doing the work. There's something almost poetic about this, even if poetry isn't what we're after tonight. The universe has arranged things so that the two most dramatically conflicting descriptions of the same event, she crossed, she never crossed, can both be true, and no experiment can ever be done that reveals them to be in conflict. The boundary between the frames is the horizon itself, and the horizon is exactly the barrier that prevents the experiment from being run. It is not magic. It is not a convenient coincidence. It follows from the mathematics, from the causal structure, from what it means for information to travel through curved space-time. But the result has the quality of a riddle that dissolves on inspection, leaving not confusion, but a kind of deepened clarity. The question, did she really cross, was always carrying a hidden assumption that there is a universal account of events, a God's eye view, a single authoritative ledger in which the answer is written. General relativity removes that assumption, and once it is gone, the question doesn't become unanswerable, it becomes unnecessary. Both answers are the whole answer from where each observer stands. Now, let's stay with you outside for just a little longer, because there is another piece of this picture that belongs here, and it is one that makes the strangeness very personal. Suppose you are not watching from a great distance. Suppose instead you are hovering just outside the horizon, not falling, hovering, which means you are firing engines constantly, exerting tremendous force to resist the pull of the black hole's gravity, maintaining your position just a fraction outside the Schwarzschild radius. You are not a free-falling observer, you are an accelerating one, rockets burning, position held. And here is what happens to you, physically, in real time. You age more slowly than someone far away, not metaphorically, not as an observational quirk. Actually, genuinely, measurably, more slowly. If your twin stays far out in space and you hover near the horizon for what feels to you like a reasonable stretch of time, and then you somehow make your way back to your twin is older. You have experienced less time. This is the gravitational time dilation made concrete in biological terms. Two twins, one near, one far, reunion, the near twin younger. This is the extreme version of something we already know from GPS satellites. Those satellites orbit at altitude further out of Earth's gravitational well than we are on the surface. Time runs slightly faster for them, about 38 microseconds per day faster relative to clocks on the ground. It is a tiny difference, but GPS systems must account for it. If they didn't, the accumulated error would make GPS navigation useless within hours. The gravitational time dilation is not an abstraction checked in a philosophy seminar. It is corrected for every day in the software of your phone's navigation system. Near the horizon of a black hole, the same effect is not tiny. It is not a microseconds per day rounding issue. It is enormous. The deeper you hover, the slower you age relative to someone far away. Hover close enough, and years pass outside while you experience only hours. Hover close enough, and centuries pass outside. The hovering twin, the one burning rockets near the horizon, returns to find a very different universe than the one she left. Not because she traveled fast, but because she stayed close to a deep gravitational well. Time is not the same for everyone. Gravity reaches into the flow of time itself and slows it, and the closer you are to a massive object, the more it slows. This is not a metaphor, it is a measured fact, confirmed from Pound and Rebka's 22-meter tower to the orbit of GPS satellites, to the timing of signals from binary pulsar systems scattered across the galaxy. And at the event horizon, the dilation becomes mathematically infinite, which is another way of saying, from the distant frame, an observer hovering at exactly the horizon would appear to experience no time at all. The denominator in the redshift formula hits zero. Time, as measured from outside, stops. This is why the frozen star picture is so evocative. It is not just that the infaler's image slows, it is that the entire process of crossing, which from her frame takes a short, finite time, maps onto an infinite span of the outside observer's time. The two clocks, her and you, are not merely slightly out of sync. They are stretched apart at the horizon by a factor that goes to infinity, and yet you, watching from outside, see not infinite light. You see, as we described, a rapidly dimming signal because the photons she emits after a certain moment are redshifted beyond any practical detectability. The infinite time is there in the mathematics. The practical observation is a fade to black in under a second. Both things are real. There is one more thing to name here before we move on to what waits inside, and it is something that sometimes trips people up when they first hear about this. You might wonder, as she falls toward the horizon, does she experience the same time dilation you observe? Does she feel time slowing around her? Does she look at her own watch and see it ticking strangely? The answer is no. From her own frame, freely falling, her watch ticks normally. She feels no slowdown. The equivalence principle applies. Her freely falling frame is locally identical to floating in empty space. Her heartbeat is regular. Her thoughts are clear. Her watch says what a watch says. She has no local sense that anything unusual is happening with time as she approaches and then crosses the horizon. The dilation is not something she experiences from inside her own frame. It is the relationship between her frame and yours. It only appears when you compare the two, and comparing them, as we have been doing, requires the light she sends you to make the journey outward, fighting the gravitational well, arriving stretched and slowed and dimmed. That stretching happens in transit. It is the light's journey out that tells the time dilation story, not anything happening to her from her own perspective. This matters because it is easy to conflate two different things: the coordinate description from outside, in which time appears to stop, and the physical experience of the infaler, in which time runs normally. Both are valid accounts of the geometry. Neither is the truer one. She falls, she crosses, she does not feel time stretching. You watch. You see her slow and redden and freeze. You do not see her cross, and the universe very calmly says yes, all of this is accurate. Now something follows from all of this, something that lives in the in-between space of these two descriptions, in the region between what's comfortable and what's unsettling. We've been saying, quite confidently, that from her frame the crossing is smooth, that the horizon is locally undetectable, that the equivalence principle holds at the moment of crossing, space-time is smooth and unremarkable there, no local measurement flags the transition. This is what general relativity says. And general relativity has been right about everything it has been tested on. The GPS corrections, the Pound-Rebka experiment, the Shapiro delay, the slowing of radar signals passing close to the Sun, measured by Erwin Shapiro in the 1960s, the deflection of starlight around the Sun, confirmed during Arthur Eddington's 1919 solar eclipse expedition, the gravitational waves from merging black holes detected by LIGO in September 2015 and announced in February 2016, the signal designated GW150914, two black holes of roughly 36 and 29 solar masses spiraling together, the universe ringing like a bell. General relativity predicted the shape of that signal. The detectors found it, matching the prediction to remarkable precision. So the theory is well supported, extensively tested, and it says, smooth crossing, no drama at the horizon. But there is a problem that has been sitting quietly in the background of this whole discussion. A problem that some physicists believe is not actually quiet at all. That is, in fact, a catastrophe. A problem that, if they are right, means the comfortable picture we've been building, the smooth crossing, the complementary frames, the both are right resolution, might be wrong. And this is where the story of the black hole stops being a story about well-understood physics and becomes, with no exaggeration, one of the deepest unsolved disputes in theoretical physics today. To understand it properly, we need one more piece of background, one more concept, and it is one that has been in the shadow of everything we've discussed so far, present but unnamed. What happens to information? Not information in the everyday sense, not the kind stored on a hard drive or written in a letter. Information in the deep physical sense, the complete description of a physical system, every property of every particle, every quantum state, the full specification of what something is. In quantum mechanics, which is our best theory of the very small, information of this kind is conserved, always. A fundamental rule called unitarity says that the complete quantum state of a system evolves in time in a reversible way. If you know the final state of a system, you can always, in principle, run the equations backward and recover the initial state. Nothing is permanently erased. The universe keeps its ledger. This sounds abstract, but it has very concrete implications for black holes, because when you throw something into a black hole, where does its information go? Stephen Hawking showed in 1974 that black holes are not perfectly black. Quantum effects near the horizon, specifically the behavior of quantum fields in curved space-time, cause black holes to emit radiation, very faint, very cold radiation. This is called Hawking radiation. For a large astrophysical black hole, the temperature is absurdly low, on the order of 60 billionths of a degree above absolute zero for a solar mass black hole, far colder than the cosmic microwave background radiation that fills all of space. So right now, today, astrophysical black holes are absorbing more energy than they emit, growing rather than shrinking. Evaporation would only dominate in the extraordinarily distant future. For a solar mass black hole, the evaporation timescale is roughly 10 to the power of 67 years. A number so large it makes the current age of the universe look like a rounding error. But in principle, eventually, a black hole evaporates. It shrinks, it gets hotter as it shrinks because Hawking temperature is inversely proportional to mass. Smaller black holes are hotter, and at the end, on a timescale no universe has yet been patient enough to observe, it is gone. Now, what happens to the information that fell in? Hawking's original calculation suggested that the radiation emitted during evaporation is purely thermal, random. It carries no information about what fell in. A black hole formed from a collapsed star and a black hole formed from an identical mass collection of rubber ducks would, according to this calculation, emit identical radiation. The information about the difference between the star and the rubber ducks would be gone, destroyed, permanently erased from the universe. This is a violation of unitarity. It breaks the quantum mechanical rule that information is conserved. Hawking initially believed this was simply a real consequence of having black holes in a universe governed by quantum mechanics, that the evaporation really did destroy information and quantum mechanics needed to be modified to accommodate it. Others disagreed strongly. The information paradox became one of the central arguments in theoretical physics. Hawking on one side, Susskind and others arguing that information must be preserved, that the thermal appearance of Hawking radiation is misleading, that somehow the information is encoded in subtle correlations within the radiation, that Hawking's calculation was too crude to capture. In 2004, Hawking revised his position. He announced at a conference in Dublin that he believed information was preserved after all, that the quantum gravitational effects he hadn't properly accounted for would ultimately restore the unitarity the equations seemed to violate. He conceded a bet he'd made on the question. He paid it with an encyclopedia because the bet had been that information was lost, and he was now saying it wasn't. But he did not provide the mechanism. He could not point to exactly how the information gets out, exactly how the Hawking radiation encodes everything that fell in. He changed his position on the conclusion without fully solving the puzzle, and the puzzle remained. And then in 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, whose names you can remember by the acronym AMPS, sat down to think carefully about what all of this implied, and they found something that disturbed them. They found that 3 things cannot all be true simultaneously. The first is the equivalence principle, the smooth crossing, no drama at the horizon. The infalla passes through freely, her frame locally identical to empty space. The second is unitarity. Information is preserved, the Hawking radiation carries out everything that fell in, the ledger is kept. The third is a basic principle of quantum field theory, which says that a freely falling observer near the horizon should see the vacuum, empty space, not a bath of high-energy particles. These 3 things, AMPS showed, form a mutually inconsistent set. You cannot have all 3 at once. The mathematics, when you push it carefully, produces a contradiction. At least one must go. And their proposed resolution was startling. They suggested that what must go is the smooth crossing. Instead of a freely falling observer sailing through the event horizon in quiet continuity, perhaps the horizon is the location of something they called a firewall, a wall of high-energy radiation, an intense, violent concentration of quantum energy right at the boundary. And the infalling observer, upon reaching the event horizon, would be incinerated immediately, violently, completely, not by tidal forces, not by spaghettification, but by a firewall of quantum energy waiting precisely at the horizon. This, if true, would mean that everything we've described about the smooth crossing, about the equivalence principle holding at the horizon, about no local experiment revealing the moment of passing through, is wrong. The comfortable complementary picture, yours and hers, both valid, no contradiction, would fail, because she would never make it inside. She would be destroyed at the boundary. The infalla's frame would not quietly disagree with yours and then become inaccessible. It would simply not exist beyond the horizon. There would be nothing inside to compare to your outside view. The problem of 2 conflicting descriptions would be resolved, but in the most brutal way imaginable. The physics community did not quietly accept this. The firewall paper generated enormous argument. Papers appeared in response, many of them arguing that AMPS had made an error in how they applied quantum mechanics near the horizon, or that complementarity needed to be extended in some subtle way, or that the argument revealed something deep about the structure of spacetime that we don't yet understand, rather than a genuine prediction of violence at the horizon. Some physicists following the work of Samir Mathur proposed a different kind of resolution entirely. Mathur had been developing a framework called the fuzzball program, working from string theory. In this picture, the black hole has no smooth interior at all. It is not an empty region of curved space-time with a singularity at the center. It is instead a quantum object that fills the entire region up to the horizon with a complicated horizon-sized ball of quantum structure. A fuzzball. There is no vacuum interior, there is no smooth passage through. The surface of the black hole for a fuzzball is a physical structure, and what interacts with it does not enter a smooth interior, but encounters that quantum surface directly. In the fuzzball picture, the comfortable image of a smooth crossing is also gone, but for different reasons than the firewall. These proposals, the firewall and the fuzzball and others besides, share one important characteristic. They are not settled, they are not resolved. None of them has been shown to be definitively correct. None has been definitively ruled out. The argument continues among some of the best theoretical minds in the world about what actually happens when you reach the event horizon. This is genuinely the frontier. Not a cleaned-up version of things we mostly understand, not a puzzle that somebody is just about to solve, a real, live, hard argument at the edge of what physics can currently say. And this is worth staying with just for a moment because it changes the character of everything we've described tonight. We've been telling a careful story. You feel nothing as you cross. They see you freeze and fade. Both descriptions are valid. The geometry enforces the consistency. The complementarity principle wraps it all in a kind of elegant coherence. That story is what general relativity says when you apply it without quantum mechanics. The moment you bring in quantum mechanics, the moment you ask about unitarity and information and Hawking radiation and what quantum fields do near the horizon, the elegant story develops cracks, deep ones. And the physicists working on those cracks do not agree on how to seal them or whether the whole structure of the story needs to be rebuilt from scratch. So when you ask truly and carefully what happens when you fall into a black hole, you are asking a question that sits at the intersection of two enormously successful theories, general relativity and quantum mechanics, that near the horizon, in the deep regime where both apply simultaneously, have not yet been reconciled into a single consistent answer. We do not have a complete theory of quantum gravity, not yet. String theory, loop quantum gravity, and other approaches are all attempts in that direction. None has been confirmed by experiment. None has resolved the firewall paradox to general satisfaction. The question remains open, which means that the story we've been telling, two frames, both correct, smooth crossing for her, frozen image for you, has to carry an asterisk. A careful, honest asterisk that says, this is what we believe based on the best theory we have for spacetime at large scales. At the quantum level, near the horizon where spacetime and quantum mechanics interact in the most extreme way known to physics, we are genuinely uncertain about what the correct description is. This is not a failure, this is science working as it should. The theories push us to their edges. At the edge they find each other, and where they meet, they produce questions neither can answer alone. And those questions are the frontier, the productive uncertainty that drives the next generation of ideas. And so here we are, floating gently in the space between two great frameworks, watching the question of what happens at the event horizon hang in the air, unresolved, fascinating, one of the deepest puzzles the universe has given us to work on. The frozen star hangs at the edge of what we can see. The infaller, in her own frame, has already gone beyond. And somewhere in the middle, in the territory between those two true descriptions. Quantum mechanics is waiting to tell us something we do not yet know, and that is where we find ourselves now, and she's inside. In her own frame, she crossed the horizon. The universe behind her is still there, still visible through a narrowing cone of light above her head, but she's inside. And the geometry of space-time in here is different from anything she's ever experienced, different in a way that doesn't feel different at all at first. The air, if she had some, would feel the same. Her heartbeat, if she measured it, would seem normal. There is no alarm, no klaxon, no indicator light blinking red. Nothing in her local experience tells her anything has changed, but something has changed, something enormous. The direction she was falling is no longer quite a direction in space, it has become a direction in time. Let that settle for a moment. We're used to thinking of the future as something that unfolds while we stay put in space, more or less. You sit in a room and time flows forward. The room is a place. Tomorrow is a time. Space and time are different things with different characters. You can turn around in space. You cannot turn around in time. Inside the horizon of a black hole, that familiar sorting breaks down. The singularity, which we're tempted to picture as a point at the center, a tiny dot somewhere ahead of her in space, a destination she could perhaps steer around, is nothing like that. In the geometry of the interior, the singularity is not a place. It is a moment. It is in her future the way tomorrow morning is in yours. And you know what you cannot do about tomorrow morning. You cannot accelerate past it. You cannot drive around it. You cannot thrust your way away from it. Tomorrow morning will arrive. That is what it means to be in your future. So it is for her. In there. The singularity is in her future. Every direction in the interior, every way she could point a thruster, every maneuver she could attempt, curves inevitably toward that future moment. There is no sideways, there is no back. The singularity is not the drain at the bottom of a funnel she's spiraling toward. It is the far end of her timeline, approaching the way Thursday approaches Wednesday, the way the last page of a book approaches the first. This is what physicists mean when they say the radial direction inside a black hole becomes time-like. In the exterior, outside the horizon, the radial direction, the direction pointing toward the black hole's center, is a direction in space. You can choose not to go that way, you can orbit, you can move sideways, you can boost away. Space-like directions are negotiable. Time-like directions are not. Inside the horizon, that particular direction has switched category. It is now time-like. The future is toward the center, full stop. And if you try to accelerate away, something counterintuitive happens. By fighting the infall, by firing your engines to push outward, you actually change your trajectory in space-time in a way that brings the singularity closer in your proper time. You arrive sooner. The most you can do in terms of extending the time you have inside is free fall. Do nothing, let the geometry carry you. That gives you the longest possible interval between crossing the horizon and reaching the end. For a non-rotating model of Sagittarius A, the black hole at the center of our galaxy, with its roughly 4.3 million solar masses, free fall from the horizon inward lasts on the order of tens of seconds. Commonly, the figure cited for a non-rotating approximation is something like 19 seconds. And that figure matters not because it's exactly right for a real spinning black hole like Sagittarius A, which would be described by the more complex Kerr geometry rather than the simpler, non-rotating Schwarzschild model, but because it tells you something about the scale. You don't wink out instantly. You have time, a real, experiential, clock-ticking span of time during which you are alive and conscious and aware. 19 seconds of wondering what the singularity will feel like before it arrives. That is an extraordinary thing to sit with. And here's something else she will not experience that popular imagination tends to add in, a dramatic embellishment that turns out to be wrong. She will not see the entire future history of the universe flash before her eyes. This is a surprisingly common image in discussions of black holes. The idea goes like this: because time outside runs faster and faster from her perspective as she falls in, surely she would see all of the external universe's history, every star that forms and dies, every galaxy that drifts away, the whole cosmic future compressed into the moments before she reaches the singularity. A final cinematographic gift from the universe, everything that ever happens, seen in one rush. But this isn't how radial infall works. The geometry doesn't arrange it that way. The light she receives during her fall into Sagittarius A comes from a finite window of time in the external universe, not from its entire future. The light she would see converging from above as she falls doesn't bring infinite amounts of the future with it. The universe outside goes on without her, but she doesn't watch the whole story. She sees a small window, a relatively brief stretch, not the death of the last star billions of years hence, not the final evaporation of the last black hole, just a narrow corridor of light arriving during those 19 seconds, compressed and blue-shifted, strange but not infinite. The real thing that awaits her at the end of those 19 seconds, or whenever her particular interior journey concludes, is the singularity. Now, the singularity. In the general relativistic description, the singularity is where the equations break. Space-time curvature, the bending and warping of the geometry that produces gravity, doesn't merely become large as she approaches the center. It diverges. The mathematics produces an infinity. And we should be honest with ourselves about what that means. It does not necessarily mean that nature produces a physical infinity. An infinity in the output of a calculation is very often the mathematical equivalent of a shrug. It means the theory you're using has been asked a question it isn't equipped to answer. It has reached the edge of its own domain of validity. General relativity is spectacularly accurate over an enormous range of scales and conditions. The predictions it makes, tested by LIGO's detection of gravitational waves, confirmed by the precision of the event horizon images from the Event Horizon Telescope, verified by GPS systems, and by laboratory measurements of gravitational redshift in experiments like the Pound-Rebka experiment, are confirmed to extraordinary precision. But near the singularity, the curvatures and densities involved reach regimes where quantum effects, the physics of the very small, become important, and general relativity doesn't know how to talk to quantum mechanics. It wasn't built to. The two theories live in adjacent territories, and the singularity sits precisely at the border where both are needed. Physicists widely regard the singularity not as a literal point of infinite physical density, but as the place where GR runs out of road. A theory of quantum gravity, something we do not yet fully have, would presumably replace the singularity with something else, something finite, something physically real. What that something is, we don't know. String theory offers proposals, loop quantum gravity offers others, but none of these proposals has been confirmed by observation. The singularity, in the honest scientific sense, is a bookmark that says, here is where we stop understanding. Here is where the next theory begins, which means the journey ends, not with a known destination, but with an honest unknown. So she has crossed the horizon feeling nothing, lived on for seconds inside, and approached an end that our best current theory cannot describe. And the person watching her from a safe distance has watched a different story entirely. The slow fade, the redshift, the freeze. Two stories, both real, but why? We've been circling that question, now let's land on it. The answer has a name in physics. It's called black hole complementarity. And the people who worked it out most carefully were the theoretical physicists Leonard Susskind and Gerard T. Hooft. building on ideas that had been developing through the late 1980s and into the 1990s. Here's the problem that complementarity was designed to solve. From the outside, you watch her fall in. You watch the image of her slow and redden and freeze and fade. From your perspective, she never quite crosses. Now, what happens to the information she carries? The particular arrangement of atoms in her body, the patterns of her thoughts, the contents of what she had for breakfast, all the quantum information that makes up her physical self. If she falls into the black hole and the black hole eventually evaporates through Hawking radiation, what becomes of all that information? Stephen Hawking proposed in 1974 that black holes emit thermal radiation. Not because matter falls out, matter can't fall out, nothing can escape from inside the horizon, but because of quantum mechanical effects near the horizon. In quantum mechanics, empty space isn't really empty. It's a seething background of virtual particles, particle-antiparticle pairs that flicker briefly into existence and then annihilate each other. Near the event horizon, something strange happens. One member of such a pair can fall in while the other escapes, and the escaping particle carries away a tiny amount of energy. Over vast spans of time, this process slowly drains the black hole of mass and energy. The black hole shrinks very gradually, and eventually, in the unimaginably distant future, it evaporates entirely. For a black hole of one solar mass, the evaporation timescale is on the order of 10 to the 67th years. That's a 1 followed by 67 zeros. The present age of the universe is about 14 billion years, roughly 10 to the 10 years. We are talking about timescales so much longer than the current age of the universe that the comparison is almost meaningless to express in words. Real astrophysical black holes, the ones LIGO detects merging, the ones the Event Horizon Telescope photographs, are currently growing, not shrinking. They absorb more from the cosmic microwave background and surrounding matter than they radiate as Hawking radiation, because the Hawking temperature of a stellar mass black hole is about 60 nanokelvin, far colder than the 2.7 Kelvin of the cosmic background. Evaporation is a future phenomenon inconceivably far off, but the paradox Hawking radiation creates is sharp and important right now, regardless of the timescale. Hawking's original calculation suggested that the radiation coming out is purely thermal, random. It carries no information about what fell in. All the quantum information that made up everything that ever fell into the black hole, every star, every gas cloud, every particle, every person who might hypothetically have crossed the horizon, would simply be gone when the black hole finally finished evaporating, destroyed, and that is a catastrophe from the perspective of quantum mechanics. Quantum mechanics is built on a principle called unitarity. The idea is that information is preserved. Physical processes can scramble information, can shuffle it, and hide it in correlations so complex they're practically inaccessible, but they cannot erase it. The total information content of the universe is conserved, the same way energy is conserved. If you know the complete quantum state of a system at one time, you can, in principle, reconstruct what it was at any earlier time or calculate what it will be at any later time. Information doesn't disappear. Hawking's calculation said it does, at least in the presence of a black hole that eventually evaporates. And that put two of the most successful theories in physics, general relativity and quantum mechanics, into direct, unresolved conflict. This is the information paradox, and it's one of the most important open problems in fundamental physics. Now, Hawking himself, for years, maintained that information really was destroyed in black holes and that quantum mechanics would have to be modified. He made bets on this. The physicist John Preskill took the other side, arguing information had to be preserved. In 2004, after new theoretical work suggested that the information does escape in subtle correlations in the Hawking radiation, Hawking conceded. He came around to the view that information is preserved. He paid off the bet, but he couldn't say exactly how the information gets out, and neither can anyone else with complete confidence. The mechanism remains genuinely contested, and here is where complementarity comes back in. Susskind and 't Hooft's proposal goes like this. From the outside, she never crosses the horizon. Her information, in the outside frame, is scrambled across the horizon surface and eventually re-emitted in the Hawking radiation, encoded in the outgoing radiation, in principle preserved. From her own frame, she crosses smoothly. Her information crosses with her and eventually hits the singularity. These two descriptions seem to contradict each other. In one, the information is outside, in the other, it's inside. Both can't be true simultaneously, can they? They can, says complementarity, because of one crucial fact. No single observer ever has access to both descriptions. You cannot be outside watching the Hawking radiation and also inside with her. The moment you follow her in, you lose the ability to observe the outside. The moment you stay outside, you lose the inside. No single observer can collect enough information to demonstrate the contradiction. The two descriptions are complementary in the precise quantum mechanical sense. They describe the same physical situation from two frames of reference that cannot be simultaneously occupied. Think of it like this, imperfectly but helpfully. In quantum mechanics, you can describe an electron's position or its momentum, but not both simultaneously with arbitrary precision. The two descriptions are complementary. They apply in different experimental contexts. Neither is the more real one. They are two valid descriptions of the same object depending on what question you're asking. Black hole complementarity says something similar. The inside description and the outside description are two valid accounts of the same events, applicable to two different observers who can never compare notes. No experiment, no measurement, no thought experiment within the laws of physics as we know them allows you to catch the contradiction by holding both descriptions simultaneously. This is also connected to the no-hair theorem. From outside a black hole, the only things you can know about it are its mass, its electric charge, and its angular momentum. That's it. All the rich detail of everything that ever fell in, every distinct configuration of matter and information is hidden from the exterior. The theorem says the exterior gravitational field doesn't care. 3 numbers, that's all. And this is exactly what makes the information paradox sharp. Everything fell in. The outside sees only 3 numbers. Where did all that distinctness go? Complementarity answers. It's in the Hawking radiation in principle, though scrambled beyond any practical hope of recovery. Inside, it's in the infalling matter. But these two answers apply to two different observers. No single observer needs both. And for many years, this was a satisfying enough answer. Contentious, but satisfying. It preserved quantum mechanics, it preserved general relativity's predictions for the infaller's experience, and it placed the apparent contradiction safely beyond experimental reach. Then, in 2012, 4 physicists decided to push harder. Their names are Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully. Their paper is known by their initials, AMPS. And what they argued, carefully and rigorously, is that complementarity doesn't work. That you can't have all 3 of the smooth horizon experience for the infaller, the preservation of information in the Hawking radiation, and the standard rules of quantum mechanics all at once. One of them has to give. Here's the argument. In the gentler version, Hawking radiation to preserve information must have a particular structure. The outgoing radiation particles must be entangled in the quantum mechanical sense with each other across the full history of the black hole's evaporation. This is what it takes for the information to be encoded in the radiation rather than simply lost. But quantum mechanics has another rule called the monogamy of entanglement. A particle can be maximally entangled with only one other system at a time. It can't be maximally entangled with 2 different systems simultaneously. Now, for the infaller's horizon crossing to be smooth and unremarkable, as the equivalence principle demands, and as complementarity assumes, The particles right at the horizon need to be entangled in a particular way, with partners on the other side of the horizon, the interior partners. And this is part of what makes the vacuum at the horizon look like ordinary, empty space, rather than a boiling mess of radiation. But if those same particles are also required to be entangled with the outgoing Hawking radiation in order to preserve information for the outside observer, you have a violation of monogamy. The same particle is being asked to be maximally entangled with two different things at once. That's not allowed. Something breaks. AMPS suggested that what breaks is the smooth horizon, that the entanglement required for information preservation destroys the entanglement required for a calm crossing. And if those interior entanglement partners don't exist, if that vacuum structure is disrupted, then what the infoler encounters at the horizon is not empty space. It's a wall of high-energy quanta, a firewall, an intense radiation field that would incinerate anything crossing the horizon instantly. Before any 19 seconds of interior freefall, before any smooth experience of being inside. This is a radical conclusion. It says the equivalence principle, one of the cornerstones of general relativity, breaks down at the horizon of a black hole, that the infaller does not get a smooth passage, that the most carefully established prediction for what she would experience, the no-drama crossing, the locally undetectable horizon, might simply be wrong, and the firewall paper has not been resolved. Years of work by some of the best theoretical physicists in the world, including responses from Susskind himself, including proposals involving concepts like ER, phi-Shafi EPR, a deep conjecture linking Einstein-Rosen bridges, which are wormholes, to Einstein-Podolsky-Rosen pairs, which are entangled particles, have not produced a consensus answer. Some physicists think the firewall is real and we need to give up smooth horizons. Some think complementarity will be saved in some refined form. Some think both the infaller and the exterior descriptions are more deeply connected than current tools can show. There are also entirely different proposals. Samir Mathur and colleagues working in string theory have developed what they call the fuzzball program. In this picture, there is no smooth interior at all. The black hole is not a region of empty spacetime with a singularity at the center. It is, down to the scale of the horizon, a dense quantum object, a ball of string-theoretic structure, a fuzzball. What looks from a distance like a clean event horizon is actually a complicated quantum surface. The infaller doesn't cross into an empty interior. She encounters the surface of this quantum object. Her information is absorbed into its structure. No firewall in the AMPS sense, but also no smooth, classical interior. A third option. None of these is confirmed. None has been tested against experiment or observation. They are genuine, serious theoretical proposals developed by brilliant people with the tools currently available, and they all represent honest attempts to resolve the same deep puzzle. We do not have a complete theory of quantum gravity, and without one, the firewall paradox sits open, an uncomfortable gap right at the intersection of the two greatest physical theories we have ever built. So the story has three layers now. The first layer is classical general relativity. Two observers, two true descriptions. Smooth crossing in one frame, eternal freeze in the other. The contradiction resolved by the geometry of spacetime itself, by the absence of any shared now across all reference frames, by the one-way causal structure that Finkelstein clarified back in 1958. This layer is solid. The predictions are confirmed. The physics here is not in doubt. The second layer is semi-classical physics, the regime where quantum mechanics is applied to fields on curved spacetime, but the spacetime geometry itself is treated as fixed and classical. This is where Hawking radiation lives. The thermal emission from black holes, the evaporation timescale, the information paradox. This layer is theoretically robust and internally consistent, but Hawking radiation from astrophysical black holes has never been directly observed. It's predicted with high confidence but remains a theoretical result, not a measured one. The third layer is fully quantum gravity, where space-time itself is quantized, and the smooth geometry of general relativity gives way to something we don't yet fully understand. This is where the firewall lives, where fuzzballs live, where the resolution of the information paradox presumably lies. This layer has no confirmed theory and no experimental data. It is the frontier. She crossed the first layer and into the second. She might, depending on which physicist you ask, run into something at the border of the third. We genuinely don't know, and there is something worth sitting with in that uncertainty. Every time in the history of physics that two successful theories have come into conflict at their shared boundary, the resolution has required a new and deeper understanding that neither theory alone contained. Newton's mechanics and Maxwell's electromagnetism came into tension at high velocities, and the resolution was special relativity. Newtonian gravity and special relativity came into tension, and the resolution was general relativity. Classical physics and blackbody radiation came into tension, and the resolution was quantum mechanics. In every case, the new theory didn't simply choose one side of the conflict. It reframed the question entirely. Whatever resolves the firewall paradox will presumably do the same. It won't simply say the infaller crosses smoothly, the outside observer was wrong, or there's a firewall, the infaller is incinerated, general relativity was wrong. It will say something about the nature of information, space-time, and quantum mechanics that neither theory currently has the language to express. Something we will look back on when we have it. The way we look back now on the moment someone realized that simultaneity is observer-dependent. We don't know what that something is, but the fact that we don't know is itself a finding. It tells us where the edge of the map is. It tells us the next great idea in fundamental physics is still out there, waiting. And from where you're lying right now, wherever you are in the world tonight, that should feel like something. Because here's the thing that the physics keeps quietly insisting on, underneath all the mathematics and the thought experiments and the debates. You are not separate from any of this. The atoms in your body, the electrons and protons and neutrons, were forged in the cores of stars and scattered through space by stellar winds and supernovae over billions of years. They assembled, eventually, into you. The space-time you're lying in, the gravitational field curving gently beneath you, pulling you softly against whatever surface is holding you up tonight, is the same space-time that curves so dramatically near an event horizon that directions in space become directions in time. The physics isn't somewhere else, it's here. It's the air in your lungs and the warmth under your blanket and the quiet weight of your own body as it begins to relax. The question of what happens at the edge of a black hole is a question about the nature of space-time and information and observation, about what it means for something to happen at all, about whether events have observer-independent reality or whether reality is always framed by who is watching. These are not questions that feel distant or academic when you sit with them long enough. They are questions about the nature of the universe you actually live in, the universe that made you, that you are continuously part of, that you are, in some exact and physical sense, a piece of. Every photon of light that has ever entered your eyes was produced by quantum transitions, by the same quantum mechanics that makes the Hawking radiation calculation possible. The same principles, the same deep laws. The black hole at the center of our galaxy, Sagittarius A, sits at a distance of about 26,000 light-years from where you're lying. Its gravity is so diluted by that distance that you don't feel it in any measurable sense. And yet it is there, vast and quiet, 4 1/3 million times the mass of the Sun, its horizon 12 million kilometers across, patient in the way that only something that freezes outside observers for the rest of the universe's life can be patient. If you fell toward it, which you are not doing, you're safely here, you're fine, just a gentle thought experiment. If you fell toward it, you would cross the horizon feeling nothing unusual, a vast and peaceful boundary that doesn't announce itself. Space-time, smooth and local and ordinary around you, even as the causal structure of the universe rearranged itself so that every direction you could ever travel from that point forward curved toward an interior future you couldn't escape. You'd have seconds, real ones, to wonder, to be astonished, to think about what comes next, and someone, impossibly far away, sitting somewhere comfortable, would watch your last image linger at the edge of darkness, slowing, reddening, stretching into the infrared and beyond, toward frequencies no instrument would ever quite detect, hovering, in principle, for the rest of the universe's life. Your final moment preserved in the geometry of space-time like an inscription on a monument that will outlast every star. Neither of you would be wrong, both of you would be right. And somewhere in the space between those two true things, in the quantum territory that no theory has yet fully mapped, something else might be happening that neither description captures, something that requires a language we haven't built yet, a question the universe is holding for whoever figures it out next. That's where the physics stands tonight, not at an ending, but at an edge, a horizon of its own. Earlier tonight, at the beginning, I asked where you're listening from, what corner of the world, what hour, whether you have a lamp still on or whether you're in the dark already, whether you're somewhere cold and wrapped in something warm or somewhere summer slow and still. I'm glad you stayed this long. We wandered through some of the strangest confirmed territory in all of science. We followed a falling observer across a boundary she couldn't feel, and we watched from outside as she hung there in reddened silence forever. And we held both pictures at once without collapsing them into one, which is the only honest thing to do. We found that the singularity isn't a place ahead of you, but a moment in front of you, the way all futures are. We found that the question of whether someone fell into a black hole has no single observer-independent answer, and that this isn't a gap in our knowledge, but a feature of the geometry of reality. And we found, right at the edge of what physics can currently say, the firewall argument sitting open and unresolved, a genuine and humbling puzzle that the best minds in the field are still working on, a sign that the map has an edge and the interesting country lies beyond it. If any of this is still turning in your mind as sleep gets closer, that's a good thing to carry with you. The universe is stranger and quieter and more precise than the popular version suggests. And you are in it, thoroughly in it, one of its arrangements of atoms and quantum states, and electrochemical processes lying somewhere on the surface of a small planet, orbiting a middle-aged star in the outer reaches of a galaxy that has a 4 million solar mass black hole sitting at its center, waiting, patient, geometrically serene. There's nothing you need to understand completely. There's no equation you need to remember. You can let the details drift away as you fall asleep, and what's left will be something simpler. The feeling that the universe is very large and very strange and very real, and that you're a part of it, not a spectator of it, and that this somehow is a comforting thing. If this slow journey through one of physics' deepest puzzles was something you enjoyed, a gentle like and a subscribe if you haven't already really does help. Nitoria is a small, independent channel, and small creators like me rely on your support to keep making these. Means more than you might think, more than you. And if you'd like to leave a word in the comments before you drift off, I'd love to know where in the world you're listening from tonight and what time it is in your corner of the dark. There's something I find quietly wonderful about knowing that these words are finding people in so many different places in so many different hours of the night. Stay as long as you like in Nitoria. Good night.